Om Swastyastu, Assalamualaikum Warahmatullahi Wabarakatuh. Syallom, Namo Budaya, dan salam sejahtera untuk kita semua. First, let me introduce myself. My name is Yudis Chrisantya. My name is 2305531063, and our lecturer is Professor Dr. Tjokorda Gde Tirta Nindhia, MT M Eng. Now we got material is Metalurgy. Then the code is TM2301, and I'm from Mechanical Engineering Technique Fakulty, Udayana University. For my presentation is from my reference is Metallurgy for the Non-Metallurgist, Seccond Edition, edited by Reardon. And now we can go to the presentation is from mechanical properties and strengthening mechanism. There is two material is mechanical properties and strengthening mechanism. For the first mechanical properties, we have definition is when a force or a combination of force are applied to a material, the material responds by deforming of the straining, often in a complex manner. For example, when the bungee jumper hoops off a platform, the bungee cord stretches dramatically, and at the same time its cross-section are decreases. Under normal circumstances, the bungee cord safely prevents the jumper from hitting the ground below. While this example describes a type of the deformation that is readily visible. Often deformation of this type cannot be observed this easily. Next, we go to the important types of mechanical properties. Different types of the mechanical properties have many of tests which is used and applied force can be employed to measure other mechanical properties as well. Additional examples of such properties include the elastic modulus, hardness, fatigue resistance, and fracture toughness. These are described subsequently in the more detail. A short list of the important types of mechanical properties include 1. Hardness as a measure of resistance to indentation. 2. Linear elastic constants that relate to strain under tensile, compressive, and shear loads. 3. Yield strength include under tensile, compressive, and shear loads, indicating the stress level required for the onset of permanent plastic deformation. And 4. Ultimate strength under tensile, compressive, and shear loads, indicating the maximum engineering stress the material can withstand without fractures. Ultimate tensile strength, or we can call UTS, typical is associated with the onset of necking of tension the specimen. As you can see in here, we can see the necking begins. It start from here. The beginning is from here. Then the necking situation is start from here. The next one is fatigue strength, indicate the level of cycling stress that cause fracture due to metal fatigue over time. And the next one is impact toughness, indicating energy absorption from load that cause very high strain rates. It's like impact. Fracture toughness, indicating resistance to fracture with persisting flow or stress raises in the geometry of a part. And the next one is high temperature, creep deformation, and stress rupture, where high temperature cause metal to permanently deform as a function of time. And the next is damping properties, and the last one is wear resistance properties. It's like due the wear mechanism such as galling, abrasion, and erosion. Next of the matter is strengthening the mechanism. There is five sub. The first one is solid solution strengthening. The second is effect of grain size. The third is cold working. The fourth is back to Dr. Williams mystery, and the last one is other important strengthening mechanism. We go to the definition of strengthening mechanism is the underlying structure of metal and alloys, be it macrostructure or microstructure, have an important bearing on their strength, ductility, and toughness. Strength of the material can be improved in various ways, as described in following section. For example, a microstructure with finer grains typically result in both higher strength and superior toughness compared to the same alloy with the basically larger gains. Other strengthening mechanisms are achieved at the expense of the lower ductility and toughness. Thus, there may also be trade-off between strength and ductility depending on the material and the application and the microstructural mechanism of strengthening. And we go to the first one is solid solution strengthening. Solid solution strengthening is a mechanism that increases the strength of a metal through to the carefully addition of specific alloying elements. The insertion of substantial and or interstitial alloying element produce a strain in the crystalline lattice of the host solvent structure because the solid atom typically have a different size than the host atoms. As we can see in here, there are a lot of size. We can go here, here, and here, and in here we can look. They have a bigger size from another one. Okay, next we go to the effect of grain size. Grain boundaries are effective obstacles to slip because the slip of dislocation in the lattice of individual grains cannot easily cross the high energy barrier of the grain boundaries. Instead, dislocations are blocked and pile up at the grain boundaries, as we can see in here. The height boundaries is on here, grain boundary. Third, grain boundaries provide a source of strengthening by pinning the movement of dislocation from the one grain to the another. It's like from the one grain to the another grain. Smaller grains in polycrystalline material also mean to that greater percentage of the material consists of grain boundaries for the strengthening. And next one is we go to the cold working. If metals is deformed at the room temperature or up to approximately on the 0.3 Tm, where Tm is the melting point on the absolute temperature scale, the microstructures become deformed due to the cold working, also known as work hardening or strain hardening. During the cold working, most of the energy is dissipated in the workpiece as heat. However, as much as 10% of the energy is retained as stored energy within the metals. In the form of vacancies, dislocation, and the stacking faults, the amounts of the stored energy increase with greater amount of deformation and lower working temperature. Cold working greatly increase the number of dislocation. Normal dislocation is like densities on the order of 10 power 6 to 10 power 7 centimeter cubic are increased to 10 power 8 to 10 power 11 centimeter cubic during the cold working. In the cold working, we can get 3 distinct processes can occur during annealing. The annealing is often employed as an intermediate step in the cold working process to reduce the internal stresses in the material and increase its ductility so that it can undergo further cold working without introducing macroscopic defects such as crack. During annealing, 3 distinct processes can occur. 1. The recovery, which relieves some of the stored internal strain energy by rearrangement of the dislocation into lower energy configuration without any change in the shape of the orientation of grains. And the second one is recrystallization, which is the replacement of the badly deformation cold worker gains by new strain-free gains. And the third, there is less grain growth, which occurs when some of the recrystallized grains grow at the expense of the other recrystallized grains. Okay, so next we can go to back to Dr. Wilm's mystery. As you know, the good doctor discovered a process now known as solution heat treating and natural aging. He also designed an alloy that is duralumin suitable for strengthening by this process in what is now known as precipitation hardening. There is 3 zones of the hardness. The basic states of the precipitation hardening are illustrated in the figure of here. We can see that there is 3 zones, zone 1, zone 2 and zone 3. With hardness plotted against time, the increase in hardness with time is known as precipitation hardening or edge hardening. Okay, so we can go to the zone 1. In the zone 1, sub-microscope precipitate particles are being formed as the alloy attempts to reach equilibrium. Solid atoms diffuse through the solvent lattice and segregate to form a few very small particles. So they can form a few very small particles. As states in the weak solute, atoms are grouped or rearranged so they can begin from a precipitate. This results in a slight increase in hardness. Okay, now we next to the zone 2, the maximum hardness. Maximum hardness is reached. The solid atoms move about and from small particles remains coherent with the aluminum lattice. Strength increase significantly in here. Okay, the last one zone is zone 3 orange. The precipitates grown in the size with continued aging and tend to become non-coherent. The loss of coherence reduces lattice stress, so resulting in decreased hardness. Now we next to the other important strengthening mechanism. The definition dispersion strengthening is an active mechanism in alloy intended for use at intermediate and elevated temperatures. The difference lies in the precipitates themselves. The particles are chosen because of their thermal stability, that is, their resistance to particle coarsening or growth at high temperature. In contrast, the edge hardening, there is heat treatable aluminum alloys consist of the precipitates, the second phase of dispersions that are not particularly thermally stable. Dispersion strengthened alloy are usually those that contain a dispersion of particles with extremely low solubilities and diffusion rates in metals. An example of a dispersion strengthening based of high temperature application are the rare earth oxides used in producing oxide dispersion strengthened, or we can call ODS alloys. In these ODS alloys, the solubilities of both the rare earths and oxygen tend to be very low in typical metals. It's like nickel and aluminum. And the diffusivities of the rare earth elements are also low. And that's all our my presentation. Forgive me when there is some problem, and I hope that can be learning for all of us. Thank you. And Om Santi 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 Om. Assalamualaikum warahmatullahi wabarakatuh. Syallom, Namo Budaya, dan salam sejahtera untuk kita semua. Thank you.